Alright, so we're starting 6.3, which is the next section that talks about and brings in a new form or a new method of finding the integration or finding the antiderivative of an integral. And it's called integration by parts. Let's jump right into it. Alright, so if we were to start with the product rule, we know that the derivative with respect to x of u times v is the first times the derivative of the second plus the second times the derivative of the first. And we can go through and multiply both sides by dx and get rid of that. And so we end up with duv equals u times dv plus v times du. If we move the v du to the other side and then we go ahead and we flip sides, then we can integrate both sides and we end up getting a situation where we're integrating u dv is and that's equal to the integral of duv, which we're going to integrate a derivative, which means we're going to end up with just times just uv minus v du. So when those cancel out, the integral and the derivative cancel out, we end up with the integral of u dv is equal to uv minus the integral of v du. Now, this is the integration by parts formula right there. That's what you're going to use. Now, in this case, you're going to notice that you've got u's and v's. In the last section, 6.2, we talked about u substitution. Well, u substitution, you only had to choose one, then you took the derivative of it and got the du with respect to dx, and were able to solve those and interchange and plug in and all that stuff. This one, you're going to have to choose a u, and you're going to have the rest of it be the dv. And then you're going to integrate the dv to find v, and we're going to differentiate the u to find du. And then we can fill all this stuff in over here on this other side. Well, it's going to make a lot more sense when you actually see it, so let's go ahead and look at it. The way we're going to choose our things is this. We're going to choose u that's going to differentiate to 0 more than likely. And our dv is going to be something that we hope is going to be, and we want to choose it so that it's easy to integrate. Because that's going to allow us to find all the stuff and fill in all the stuff over here. Now, the integration by parts formula is a product rule for integration. Now, you want to choose u. This is the best way that I've actually found it. You want to choose u in this order, using the word lipid. And these are just it's the first letters of the type of function you want to choose. So you're going to choose your u first using this. L is logarithms. I is inverse trig functions. P is polynomials. E is exponential functions. And T is trigonometric functions. Now, inverse trig and trig functions are very, very different. So understand, that's the situation. You want to inverse trig is way up here on front, where a regular trig is the very last. That's the last ones you want to choose for u, because when you differentiate those, they just go through cycles typically, or they even get bigger. I mean, think about the derivative of secant. It becomes secant tangent, and then you have a product that you got to take the derivative of next time. So you want to choose it in this order. Logs are going to be the first choice, inverse trig functions the second choice, polynomial third choice, and trig is the absolute last. Alright, so let's do an example here. We've got the integral of x times cosine x dx, and if we go through our list with lipid, we know we're going to choose. There are no logs, there are no inverse trig functions, but we do have a polynomial. Even if it's a single term, a monomial is a polynomial. So I'm going to let u equal x. And if I let u equal x, that means that dv is equal to everything that's left. So cosine x dx. So I need to find du, and that's going to be 1 dx, or just dx. And then I need to find v, which means I need to integrate this. So if I integrate cosine, I'm going to end up with sine x. All right, so at that point, we've done everything we need to do. So all we need to do is plug this thing in. Now remember, the integral of u dv is equal to u times v minus the integral of v du. And all we're going to do is just plug all that stuff in. So here we've got the integral of x times cosine x dx. That's my integral of u dv, is equal to u times v, so x times sine x, minus the integral of v times du. Well, v is sine x, and du is just 1 dx, or dx. All right, so here's the whole benefit of the integration by parts formula. Now we've broken this up, we've expressed this in terms of u's and v's, and du's and dv's, but now we've got a situation where we have a much simpler integral here to solve than what we started off with. So we would just go ahead and finish that thing up, and we would have x times sine x minus, now what's the integral or the antiderivative of sine x? Well, that would be negative cosine x. So negative, subtracting a negative is a plus. We end up with cosine x, and of course we put our plus c since we don't have upper and lower bounds. You'll notice I didn't put plus c with this. You're only going to put the plus c when you've finished all of your integration. All right, let's do another example. In this case, we're going to do the integral of natural log of x dx. Now, you're looking at this one and you're thinking, well, wait a minute, that only has one term. Yes and no. We can always put an extra term of 1 in there. But when we do this, we're going to end up u and dv, of course. And u, according to Lippitt, logarithm, there we go. So we've got natural log of x. And then dv is everything else, so dv equals dx. So when we do and solve the rest, so du is going to equal 1 over x dx, derivative of natural log of x, times dx. And then v is going to be the antiderivative of this side, the antiderivative of this side, equals x. All right, so once again, integral of, so that's an ugly integral. That's not much better, is it? Integral of u dv equals u times v minus integral of v du. So when we plug everything in, the integral of the natural log of x dx, that side there, is equal to u times v, natural log of x times x. I'll write that x times the natural log of x, minus the integral of v du. Integral of v is x, so integral of x times du, which is 1 over x dx. And what happens with the x times 1 over x? Well, that's going to cancel out to leave you with just 1 dx. And what's the integral or the antiderivative of 1? It's just going to be x. So we end up with x natural log of x – x plus c. x times 1 over x gives us just a big fat 1, and integral of 1 dx is just going to be x. All right, let's do another one. This one's going to be a little more complicated, but it's not that bad. All right, we got x squared e to the x, and once again, remember to lip it. Logarithms, we don't have any. Inverse trig functions, we don't have any. Polynomials, yep we do. We've got a single term polynomial in x squared. So u is going to equal x squared, which means that dv is going to equal e to the x dx. So when we go and find these, du is going to equal 2x dx, and v, what's the antiderivative of e to the x dx? Well, it's just going to be e to the x. All right, now I'm not going to write everything out again, so we're just going to start off with the u times v. So u times v minus the integral of v du. All right, so we've got x squared e to the x minus the integral of v e to the x du times 2x dx. All right, and that simplifies down into x squared e to the x minus 2x e to the x that's in the integral times dx. Now, you're going to notice here that we have a situation yet again where this is not something that's actually going to be easy to do. So we're going to have to actually do integration by parts again. But we're only going to do it on this part right here. So if we look at this part right here, we have a u that's going to be 2x, and we have a dv that's going to be e to the x. That's not a good e to the x, is it? dx. All right, so when we do du, we're going to get 2 dx, and when we do v, we're going to get e to the x again. And then we're going to write everything down again. I'm going to continue this in blue, but I'm going to write the red in what our integration by parts is. So this tags along. It's not part of what we're actually doing now, but it's still a part of the solution of the original problem, don't forget. So x squared e to the x minus, and then I'm going to put brackets, and this is what we're doing the integration by parts on. So u times v, 2x e to the x, minus v e to the x, the integral of e to the x, times du, which is 2 dx. Now, of course, we can pull that 2 all the way out front there. So this is going to be x squared e to the x, coming from right here. Oh, hold on. Never mind. I need to change something here. I told you I was going to do something, then I didn't. This all right here should be in red. Okay, so that's the part that came from my integration by parts the second time. All right, and then if I write this down again, I've got x squared e to the x. That comes from this part. And then distribute this minus all the way through. So minus 2x e to the x. And then minus times a minus gives us a plus. Now, what do we know about this? Well, we brought the 2 all the way out front. And what's the antiderivative of e to the x dx? Well, we've done that a couple of times already. It's just going to be e to the x. And then, of course, we have to include our plus c. So there's our solution. So you can use your integration by parts multiple times. As long as you have an integral that's not an easy to do integral, but it still fits the exact same thing of the product of a couple of functions, you can do integration by parts again and again and again. All right, so this one, we've got e to the x cosine x dx, and I'm going to go ahead and tell you this one's actually going to be a little bit of a trick, but it's not that big a deal. So looking at this and using Lipit, what is your u going to be? Well, we don't have any log functions. We don't have any inverse trig functions. We don't have any polynomials. We do have an exponential, though. So that's going to be my e to the x. Or that's going to be my u as e to the x. And the rest of it is going to be my dv. So dv is cosine x dx. So when I find my du, take the derivative of e to the x, it's going to be e to the x dx. And over here, when I integrate and find what v is, the antiderivative of cosine is sine x. So now I've got my u and my v and all that stuff. So if I start writing this thing, I'm going to do u times v minus the integral of v du. So u times v is e to the x sine x minus the integral of v sine x times e to the x dx. Now, looking at this, once we simplify it, we have e to the x sine x from the first part here minus the integral, and rearranging this, I'm going to get e to the x sine x dx. Well, that's not much different from what I started off with. The trig function changed. So I'm going to have to do this thing again. But what do you notice? Every time we, well, let's go ahead and work it a little further and see what happens. So let's do integration by parts on this part right here. So for u, you're going to have e to the x again. And for your dv, you're now going to have sine x dx. So du is going to equal e to the x dx again. And v is going to equal negative cosine x. All right, so when we plug everything in, we're going to have e to the x sine x minus, and then this is where we put all this stuff right here in. So let's change colors here. And we've got u times v. So we got negative e to the x cosine x. I have the negative from the cosine I just moved out front. And then minus the integral of v, negative cosine x, du. So that minus, once again, can come to the front and make this a plus. And we're going to end up with e to the x cosine x dx again. All right, so that came from the second integration by parts. Let me change that. So the blue in here is the second integration by parts. Now let me go ahead and I'm going to rewrite this. I'm going to rewrite it in a little different way just because I want you to see something. So we started off with this. So the integral of e to the x cosine x dx, and we started working this problem and we found out that it's going to equal what we have right here. E to the x sine x negative negative, so that's a plus e to the x cosine x, and then minus the plus here is minus the integral of e to the x cosine x dx. All right, now I want you to think about that for just a second. Do you notice anything kind of weird? Well, if you don't notice it, I'm going to point it out to you. This thing right here on this side is exactly the same thing as this integral over here on this side. We have matching integrals. So what we can do, and this is kind of neat, is that, remember, that just has a value. So we can add, subtract, multiply, and divide that the same way we can any other answer. So we're going to add the integral of e to the x cosine x dx to both sides. Well, if we add that integral over here, we're going to end up with 2 times that integral. And it's going to equal everything we already have over here except for this part that we just moved. So e to the x sine x plus e to the x cosine x. Now, remember, we don't want to know what 2 of these things are equal to. We want to know what only one of them is equal to. Well, we can get by with that. It's still just math. We can divide both sides by 2. And when we do that, we've actually solved for our unknown integral. And that's what they call this, solving for the unknown integral. So we have e to the x cosine x dx, these 2's are going to cancel out, is equal to, and you could put a big 1/2 out in front of it, I'm going to leave it over 2, e to the x sine x plus e to the x cosine x, all divided by 2. So we've actually found what the answer to that integral actually is. It's that thing right there. Now, you would probably notice that if you had continued to do this, well, if the integral of e to the x cosine x gave you all this crap to begin with, what's going to happen if you do it again here? It's still going to just give you the same thing over and over and over and over again. So this is the only way that you can solve this. If you had continued on over and over and over again to do the integration by parts, you're just going to get more and more and more terms, and it's never going to get to the point where it's going to go away. The reason why? Because our u is never going to differentiate to 0. If you go back and look at our previous examples, the u here differentiated to 0, so we would not end up having 2 terms in this integral eventually. But the thing is, with e to the x and cosine x, they both are cycles. They cycle through derivative and integration and keep a value forever and ever and ever, no matter how many derivatives or integrals you do of them. So that's never, ever, ever going to go away. So that is the never-ending integration by parts if you continue going on. So this is the way you get out of it, is by solving by that unknown integral. Now, it's not always going to be 2. If this had had some number somewhere in there, you could have had up to 5 or 12 or whatever over here as a number in front of this. You'd still just move it to the other side and divide by that same number. So don't freak out if you end up getting something that has some number other than 2 over here, and you're going to add that many over here. If you ended up having 6 integrals of e to the x cosine x dx, you would just divide both sides by 6 again. So it's not going to change. It's still, guys, it's still just math. Those rules still hold true. Whoop, I did forget my plus c. Sorry about that. But yeah, you need to go back and put the plus c. All right, now there is a shortcut for the integration by parts, and it occurs if you have something that's going to differentiate to 0. And what we call this is called tabular integration, and it's because you use a table. So tabular integration works for integrals of the form where you have 2 distinct functions in there with dx, and one of the functions is going to integrate to 0 in a few steps. And the other one is able to be integrated repeatedly. Now, if those 2 things don't hold true, don't do integration by parts using tabular integration. Go as far as you can with integration by parts and see if there's some way you can solve for the unknown integral. If this does not differentiate to 0, you're going to have a table that goes on forever. If this one doesn't integrate repeatedly, you're going to run out of terms in that column before this one differentiates to 0. So you got to make sure that those two things happen. All right, so this one we've actually already done. So let's go back and we're going to look at this one again. You already know what the answer is because we did it previously. It was example 3, I think. But we're actually going to use tabular integration to do this. So this one is the one that's going to differentiate to 0 in several steps. This one's the one that's going to integrate repeatedly. So we've got x squared over here and e to the x over here. So we got x squared, 2x, 2, and 0. Over here, we're going to start off with e to the x, and the integral of e to the x is e to the x, the integral of e to the x is e to the x, and the integral of e to the x is e to the x. You just go e to the x all the way down. Now, that's the table part. Here's what you do then. You're going to go over here and you're going to start with a plus, and you're going to do alternating signs down through here. Plus, minus, plus, minus, plus, minus, plus, minus. And then you're going to draw diagonals from one column to the next. And that is you building your terms. So the first term is positive, x squared e to the x, minus 2x e to the x, plus 2e to the x. And then when the 0 is there, 0 times that would have ended anyway, you just put your plus c. So that is how you use tabular integration. And if you need to, go back and back up and see what I did here. Just the derivative of the thing that's going to differentiate to 0 in this column, and the rest of it you're going to integrate in this column. It has to integrate repeatedly. And alternating signs going down this column here. Diagonals, you got to do the diagonals. I know it doesn't show up here, but if you don't do diagonals on like a trig function one, it's not going to work. So you get used to drawing those diagonals, and then that's where you build your terms. And then once you get to the 0, that's where you put the plus c. Okay, and there's the way we did the other problem. Remember, we had to do the integration by parts 2 times and all that stuff. So tabular integration does shorten things up a bit, especially if you have to do multiple versions or multiple occurrences of the integration by parts thing. It speeds it up way quicker. All right, so let's do this one. I want you guys to try this with tabular integration. Pause the video, work it out, and then come back and see if you got the right answer. So I'm going to pause it, and I'm going to work it out. So here in just like 10, not even 10 seconds, 5 seconds, you're going to see the solution. So pause it and you try it yourself, please. That'll give you an idea if you know what you're doing with tabular integration. All right, so here's the solution that you should have. The antiderivative of x cubed sine x dx is going to be negative x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x plus c. So we start with what we started off with, derivative down this row, integral down this row, and don't forget, if you're having problems with this, remember you can do sine, cosine, negative cosine, and then that's the derivative method route. But we're doing the antiderivative, so the derivative of sine x, follow the arrow back, negative cosine x. Negative cosine x, negative sine x. Negative sine x, cosine x, and then cosine x sine x. So you go all the way back. And don't forget your plus c. All right, if f prime of x equals g of x, then the integral of x times g of x dx equals x times f of x minus the integral of f of x dx. True or false? Justify your answer. So what this is asking is, if you used f prime and g of x, if f prime of x equals g of x, would you be able to, how would you do the integration by parts thing here? So let's say we let u equal x and dv equal g of x dx. Yeah, that's not going to work, is it? So let's let f of x be u. No, sorry, g of x. Let's let g of x be u. No, that was right. I had it right to begin with. I have to think here. All right, so we get du is just dx, because that's going to be 1. And v is the antiderivative of g of x. Well, if g of x is f prime of x, then the antiderivative of f prime of x is just going to be f of x. All right, and then when we put everything together, u times v is x times f of x minus the integral of v, f of x, du. So f of x dx. And that's exactly what we got right there. So true. And remember, when you see a capital function, that's going to be an antiderivative. So this capital G of x is the antiderivative of g. All right, so you guys try that one and see if you're going to get the right thing. Check it out, try it, pause the video, and see if you get, see if this is a true or false. I'm going to give you 5, 4, 3, 2, 1, and the answer is true. It's also true once again. If you let u equal x squared, then du equals 2x dx, dv equals g of x dx, which is when we find antiderivatives, it's going to be v is equal to antiderivative of g of x, which is f of x. When you plug everything into the integration by parts formula, boom, there it is. You can bring that 2 out front of that integral. All right, so if x squared cosine x equals h of x minus the integral of 2x sine x dx, then what is the h of x right here? So if you were to do the integration by parts, what would this part right here? That, by the way, is the u times v, right? So see what you could find out. See which one it's going to be. And notice there's not a plus c here. That's why there's a plus c in everything here. So, and that kind of defeats the purpose of this integral. But anyway, you would have a plus c because you have done part of the integration, I guess. But go ahead and do the first step. Go through one process and see what that first part would be. And see if you can get it right. All right, and I'm going to show you the answer in 5, 4, 3, 2, 1. The answer is B. X squared sine x plus c. And then, so this would be x squared sine x minus the integral of 2x sine x dx plus C, or you could leave the plus C off if you were doing it without the, or to get all together. All right, that's all of 6.3. Make sure you make note of any questions you might have to ask in class. And see you soon.